Hi everyone, welcome back. This time we're going to talk about X-ray diffraction. This is, as it will turn out, a very closely related concept to the reciprocal lattice, which is what we talked about last time. X-ray diffraction is certainly very important for characterizing solid-state materials. It's also important from a basic physics standpoint when it comes to understanding things like energy gaps, which we'll talk about in the coming days and weeks. It will turn out that the basic idea behind X-ray diffraction also applies to things like energy gaps, which we'll learn about later on. So in 1913, father and son Bragg discovered that X-ray reflection from certain crystalline samples had very strong peaks as a function of the incident angle on the sample. And so they understood this by assuming that the crystal was composed of planes, each of which scatter X-rays speculatively. So the basic picture that they had in mind was that the crystal is composed of a set of planes, let's say, separated by some distance d. And if one has incident X-ray and reflected X-ray with some angle theta, the extra distance that the X-rays travel when they reflect off of this lower plane, as opposed to the upper plane, is this distance plus this distance. And it's not so hard to see that if the angle of incidence is theta, the extra distance traveled by the X-ray when it reflects off of the lower plane compared to the reflection from the upper plane is twice d sine theta. And if we're asking about the condition for a reflection peak, what we mean is there's constructive interference between these reflected X-rays. So we'll require that twice d sine theta, which again is the extra distance the lower X-ray travels relative to the upper one, is equal to an integer number of wavelengths. So n here is an integer. It's called the order of the reflection peak. So this is called the Bragg condition for X-ray reflection. Now, of course, real samples, real crystals aren't made of just planes. They're made of lattices of atoms. Though we've just talked about lattice planes, so this maybe isn't quite as much of a stretch as one might naively imagine. We also know that lattice planes are intimately connected with reciprocal lattice vectors. So there's also an important connection between reciprocal lattice vectors and X-ray diffraction, which we'll talk about now. So there's an alternate way to think about X-ray diffraction. That's called the von Laue formulation. So here, in this formulation, we don't need to imagine that the crystal is composed of planes. But what we do need to imagine is that the atom at each lattice point can re-radiate in all directions. So this is a different set of assumptions than what we assumed in the Bragg formulation. Remember there we assumed that the lattice planes reflect specularly. Here we're assuming that the solid is made of atoms, but that the atoms re-radiate in all directions. So to understand this, let's think about two scatterers in a solid. Let's assume that they're separated by some vector d here. So now let's suppose we have incident X-ray radiation coming in along a particular direction with wave vector k. So it looks like this. So we'll say that the wave vector, the incident wave vector, is characterized by some wavelength, lambda, and direction n hat. Let's suppose that we're measuring these X-rays along a different direction. Let's call it the n prime direction. So the reflected X-rays will have wave vector k prime. Here, k prime has the same wavelength, but a different direction n hat. So if you like, here is direction n, and here is direction n hat. Now let's again ask about the condition for constructive interference. In this case, we need the extra distance traveled by this outer X-ray, which is this distance plus this distance, to be an integer number of wavelengths. All right, so let me write down this. Sorry, having computer problems here. This angle here as, one moment, this angle here as theta, and this angle here as theta prime. D is the distance between these two scatterers. The extra distance over on the left is d cosine theta, which is equal to d dot n hat. The extra distance on the right is d cosine theta prime, which is minus d dot n hat. So here on the left-hand side, d and n hat are pointing in roughly the same direction. Here on the right side, they're pointing in roughly different directions. So the extra distance is minus d dot n hat prime. Okay, so the condition for constructive interference, again, is that the sum of these two distances is equal to an integer number of wavelengths. So we'll say that d cosine theta plus d cosine theta prime is equal to m lambda, where m is an integer. So let's rewrite this as d dot n hat minus n hat prime is equal to m lambda. Now let's multiply both sides of this equation by 2 pi over lambda, and we get d dot k minus k prime is equal to 2 pi times an integer m. Good? Just to recap, the condition for constructive interference is d dot k minus k prime is equal to 2 pi m. Now, in a real lattice, this vector d would be a member of the Bravais lattice itself. So we would have capital R dot k minus k prime is equal to 2 pi m, where R now is any vector in the lattice. So what this means then is that e to the I R dot k minus k prime must be equal to 1. But we've seen this before, right? Any vector such that, any vector big K such that e to the I big K dot R is equal to 1 for all big R must be in the reciprocal lattice. So the last equation tells us that we have to have e to the I, let me rewrite it here, k minus k prime dot big R equals 1, which means that it must be true that big K, a member of the reciprocal lattice, is equal to little k minus little k prime. In other words, the change in wave vector associated with the X-ray diffraction peak must be a reciprocal lattice vector. All right, again, the condition for constructive interference is that the change in wave vector is equal to a member of the reciprocal lattice. Now there's an alternate formulation of this, which we can understand as follows. So we know that the magnitude of little k is the same as the magnitude of little k prime. That's because the wavelength doesn't change. We also know that little k prime is equal to little k minus big K. So if we substitute in this expression for little k prime, we have the magnitude of little k is equal to the magnitude of little k minus big K. Now if we square both sides, we have little k squared is equal to little k squared minus twice little k dot big K plus k squared. This tells us then that little k dot big K hat is equal to big K over 2. So what this means is that the component of little k along big K, little k dot big K hat, is equal to half the magnitude of big K. So half the component of the incident wave vector along the reciprocal lattice direction must be equal to half the magnitude of that reciprocal lattice vector. So the picture that you can have to understand this looks as follows. Here's a reciprocal lattice vector, big K. Here is the incident wave vector, little k. Here's the reflected wave vector, little k prime. We'll have constructive interference whenever the tip of little k lies in a plane that bisects big K, the reciprocal lattice vector, big K. So these are called the Bragg planes. If the tip of little k is on one of these Bragg planes, if it's on a plane that bisects the reciprocal lattice vector big K, then we'll have constructive interference. And because these Bragg planes are planes perpendicular to reciprocal lattice vectors, they correspond, as you know, to real space lattice planes. So now you can start to see that there's a connection between this von Laue formulation and the Bragg formulation of X-ray diffraction. So we can see that they are, in fact, identical in the following way. So let's imagine now that I'm just going to redraw the diagram that we had before. So here is big K. Let's imagine that we have a little k and a little k prime that satisfy the von Laue condition. So we can draw them in the following way. So here is, I'm going to draw little k like this, and I'm going to draw a little k prime like this. If you like, you can draw minus little k up here. And the right side of this drawing should convince you that the change in wave vector is indeed a reciprocal lattice vector. Okay, let's imagine that we call this angle here theta. We can write, based on our theorem before, which connects lattice planes and reciprocal lattice vectors, the magnitude of big K as 2 pi n over d, where n is an integer, and d is the spacing of a family of lattice planes perpendicular to K. Remember, we had a theorem that said for every reciprocal lattice vector, there exists a family of lattice planes, and the spacing of these lattice planes is equal to 2 pi over K, where K is the length of the shortest reciprocal lattice vector. So this is using this theorem that we wrote down before. Okay, now back to this picture. The von Laue condition requires that the projection of little k along big K is equal to half the magnitude of big K. So if we think of theta as our angle of incidence here, you can see that this distance here, which is the projection of little k along big K, is k sine theta. This should be equal to big K over 2. So let's use our definition of K as 2 pi over lambda times sine theta is equal to, now let's use our expression of the length of K in terms of the lattice plane spacing over here. We have pi n over d. All right, rearranging just a little bit, we have twice d sine theta is equal to n lambda, where again n is an integer. This is exactly the same as the Bragg formulation that we talked about later. So you see that the Bragg and von Laue formulations are identical, and these Bragg planes that we talked about before indeed correspond to the real space lattice planes. Good. So let's talk about how X-ray diffraction is measured in practice. Let me parenthetically add that this discussion of Bragg planes and X-ray diffraction again will come back when we talk about energy gaps in the context of band theory. So maybe it's worthwhile noting that X-ray diffraction is important not just from a measurement point of view, but from also a basic physics point of view. So let's now finish by talking about how X-ray diffraction is measured in practice. So let's talk about something called the Ewald construction. So in general, as we saw before, constructive interference will occur when the change in wave vector is equal to a reciprocal lattice vector, big K. Obviously, there's only a discrete set of incident and detection wave vectors where this is satisfied. So you can visualize this in the following way. This is called the Ewald sphere. So let me draw some reciprocal lattice points for you. Okay. Let me draw one reciprocal lattice vector. Let's call it big K. And we know that constructive interference will occur when the change in wave vector, little k minus little k prime, is equal to big K. So let's suppose I send X-rays along this direction, little k. And for this choice of big K, I'll measure constructive interference when little k minus k prime is equal to big K. Now, if I fix a little k, if I fix the direction of incidence, and if I sweep the detection direction, that corresponds to sweeping little k prime. One way you can imagine visualizing this is if I sweep a circle, so let me pick the center of the circle as the tip of little k. Let me now draw a circle of radius k around it. So it'll maybe look something like this. So this circle corresponds to sweeping all possible orientations of little k prime. And when this is true, I will measure constructive interference. So whenever a reciprocal lattice point is on the surface of this circle or sphere in 3 dimensions, I'll measure constructive interference. So you can see that this happens infrequently. There's certainly only a finite set of points that satisfy this, it's not a large number of points. So again, I'll measure, if I sweep the direction of detection, constructive interference when a reciprocal lattice point touches the sphere. So you can increase the number of points that do this by sweeping the wavelength in addition to the direction. So that would, if you like, create, instead of a sphere, something like a shell, where if you have any point that lands inside the shell, you'll measure constructive interference. Or you can also rotate the sample itself, which would correspond to rotating all of these points with the fixed sphere. So every time one of these points passes through the sphere, you get constructive interference. So this is somewhat complicated and perhaps a little bit challenging to explain asynchronously, but maybe the point is that measuring X-ray diffraction is an important subject in and of itself, and there are lots of interesting tricks to play. So let's talk about one final topic here relating to X-ray diffraction. This is called the structure factor. So far we've only considered a monatomic lattice. Remember we said that the phase difference between two, the phase difference between the X-rays scattered by two different scatterers is d dot k minus k prime. For constructive interference, this phase difference needs to be an integer multiple of 2 pi. Now, if we have identical scatterers at different positions in a primitive cell, if we have a lattice with a basis, so suppose instead of just 1D, we have now a number of scatterers for each lattice point in each primitive cell, then the overall amplitude will contain something that's called the structure factor, which is just the sum of all of the phase factors from the different scatterers in the cell. Okay, so the idea is if we have multiple scatterers at the same lattice point, if we have a lattice with a basis, here it's a little endpoint basis. To compute the overall effect of all of these, we need to add the phase factors from all of these together, and this will be imprinted on the amplitude. The sum of these phase factors is called the structure factor. The intensity, the X-ray intensity associated with constructive interference at this reciprocal vector big K will go like S of K squared. So this is an extra intensity modulation that depends on the reciprocal lattice vector big K, which conveys some information about what happens at each lattice point. If it's not just a single scatterer, but there are multiple scatterers at each lattice point, you can look at the pattern of intensities as it varies between peaks to learn something about this. Okay, if we have different types of atoms at each lattice point, so in this last example, we were implicitly considering the case where we have multiple atoms per lattice point, but they're all the same. If we have different types of atoms, then the structure factor looks like a sum over all of these phase factors, but now there's an additional amplitude describing these different atoms, Fi of k, and this is equal to the Fourier transform of the charge density. of each species. Okay. This again actually is very much like our original definition of the structure factor, but here now we're considering how individual atoms may have charge distributions that are not like delta functions. All right, so this completes our discussion of the reciprocal lattice and X-rays. In the next set of mini lectures, we'll begin to talk about the effect of electrons in periodic potentials, and this will be one of the major topic areas of the course.